From the 1920s, quantum mechanics theory was gradually formed by the effort of physicists such as Erwin Schrödinger, Albert Einstein, and Max Born. Innovative technologies such as transistors, semiconductor components, solid-state light sources, lasers, and optical fibers have shaped the foundation of the information society we are familiar with. In recent years, the semiconductor industry has come to the end of Moore's law. The transistor and wire dimensions have been reduced to the nanometer level. At this time, a quantum tunneling effect will occur.
Hello, my name is Chen-Fang Wu. Today I'm going to be presenting my final year project on computational investigation of quantum tunneling to a double barrier. The aim of this project is to produce a model to investigate the behavior of wave packet tunneling through a barrier using numerical methods.
The time-independent Schrödinger equation for a particle in 3 dimensions is given by where h bar is Planck's constant, m is the mass of the particle, b is the potential energy, E is the energy of the particle, psi is the wave function. Since we are free to shift the origin of the potential energy scale, we will take potential energy 0 everywhere. We also assume that region is one-dimensional so that the operator reduces to the second derivative. The equation then becomes.
Here's my one-dimension result of the time-independent Schrödinger equation for a particle in a well problem using the Newton method for the lowest energy level. The special step size was 0.01. We have taken 0 volts inside the well and 1000 volts outside. The initial energy level of 2 volts, decreasing it by 0.025. The last value of E calculated here was 1.23. The above solution took a total of 36 iterations. The initial energy level of 5 volts, the value we find for the energy of the lowest earth particle level is 4.88, which is about 1% below the exact value for a well with infinitely high volts. As with the ground state energy, this difference is due mainly to the fact that the potential outside the well is not infinitely large. The above solution took a total of 10 iterations.
The time-dependent Schrödinger equation for a particle in 3 dimensions is given by. It describes how a wave function evolves over time. This is a wave packet I plotted using MATLAB. A wave packet can be used to describe a particle. A wave function is a complex form with 2 parts, real wave and imaginary wave. Both parts have identical wavelengths and frequencies. The square of the amplitude of a wave packet at a certain time or position is the probability of finding a particle at that time and position. Let's take a look at the wave packet equation. X represents the initial position. C represents the wave packet amplitude. Sigma square represents the wave packet width. K represents the initial momentum. Here are the one-dimensional results I created using MATLAB. In these animations, we will see the wave packet propagating in the different potential barrier. Wave packet travels at a constant velocity. The height of the propagating packet decreased as it moved. This is due to the wave packet spreading. The uncertainty relation tells us that all such packets will spread with time. Wave packets move to the right. The higher the potential energy, the velocity level gradually slows down. The more the left direction, the smaller the potential energy, the velocity level increased. As the wave packet moves to the right, the potential energy leads to the velocity fast. As the wave packet strikes the barrier, we can see considerable oscillation. None of the wave packets enter the potential barrier. All of the wave packets are reflected. We see the probability for the particle to tunnel through a barrier increases rapidly as the width of a barrier is decreased. The probability for the particle to tunnel through the barrier increases rapidly as the height of the barrier is decreased. The probability for the particle to tunnel through the barrier increases rapidly as the wave packet scale is made larger. A part of the wave packet was reflected, while a very small part was transmitted to the right, which is trapped inside of the well. As the wave packet incident on the cliff, we can see considerable oscillation. None of the wave packets enters negative area. The probability for the particle to transmit through the cliff increases rapidly as the width of the barrier is decreased. It is unusual to see the reflection of the wave packet from the cliff instead of dropping down. It is the nature of quantum mechanics. The probability for the particle to transmit through the cliff increases rapidly as the depth of the barrier is decreased. The probability for the particle to transmit through the barrier increases rapidly as the wave packet scale is made larger. The wave packet is incident from the left. A part of the wave packet was reflected, while a very small part was transmitted to the right, which is trapped inside of the well. Here are the two-dimensional results I created using MATLAB. In these animations, we will see the wave packet propagating in the different potential barrier.
The project was completed before the expected completion time.
At the completion of the project, I have achieved all of the goals and objectives that were set. The project received excellent and positive feedback from the supervisor. The project was able to achieve all of its objectives, and both the investigator and supervisor were satisfied with the result. The behavior of Webpacket was investigated in different potential barriers using the numerical method. The investigation has shown that there are different quantum effects such as penetration, reflection, and diffraction as Webpacket propagates in different potential barriers. Furthermore, the intensity of the quantum effect will also change after adjusting the conditions of potential barriers or Webpacket parameters. The investigations were conducted by the use of 1- and 2-dimensional simulations. Further investigation could be done by using artificial intelligence.